In this section, I will talk about an introduction to set theory. We will look at how to define a set. We're going to write sets in three different ways. Define an empty set, find the cardinality of a set, classify sets as finite or infinite, and decide if two sets are equal or equivalent. So a set is a collection of objects. In our study of sets, we will want to restrict our attention to sets that are well defined. A set is well defined if for any given object we can objectively decide whether it is or is not in the set. Each object in the set is called an element or a member of the set. The elements of the set are listed between braces with commas between the elements. This is called the roster method. The order in which we list the elements is not important. So when you write the braces look like this. I'm not very good at drawing, but I'll show you in one of the slides how to actually write it. So if we look at this example, we're going to write the set of months of the year that begin with the letter M. Is this a set well defined? Why or why not? Alright, so the months that start with M will be March and May. So this is how you would write the set. As you can see, March and May are separated by commas and they are in braces. So that was my attempt to write a brace. It looks like this. Okay. This is a well-defined set because it clearly states that the months have to start with M, and there's no opinion to it. So usually a well-defined set, a set that's not well-defined is one where you have to give your opinion. Something like list the people who are best dressed. That's opinion based. Okay, so that would not be a well-defined set. But in this case, this is a well-defined set. Sets are often labeled with capital letters. The set of natural numbers, which we call counting numbers, is defined as n, and then in that set will be 1, 2, 3, 4, and it keeps going. So those three dots that you see, that means that the list of elements continues indefinitely in the same pattern. You can also call these ellipses. The set of even natural numbers would be 2, 4, 6, 8, and it keeps going. And the set of odd natural numbers will be 1, 3, 5, 7, and the list keeps going. So we're going to use the roster method to do the following. We're going to write the set of natural numbers less than 6. Okay? Natural numbers less than 6. So that will be 1, 2, 3, 4, 5. The next one says the set of odd natural numbers greater than 4. Odd natural numbers greater than 4. So any number greater than 4 that's odd. That would be 5, 7, 9, 11, and the list will keep going. So you put your dots there. So this symbol that you see here looks like a little e. It's used to show that an object is a member or element of a set. For example, if A is the set of days of the week, we can say Monday is an element of that set. Okay, so you write Monday and then little e and then A. You can also say Friday is an element of that set. When an object is not a member of a set, we use the same symbol, the letter E, with a slash through it. Ice cream day is not a day of the week, so we can write ice cream day is not an element of set A. So we're going to decide whether or not each one of these statements is true or false. Oregon is an element of A, where A is a set of states west of the Mississippi River. So the Mississippi River is like in the middle of the United States, kind of. So Oregon is on the west coast, so Oregon will be west of the Mississippi River. So this is true. The next one says 27 is an element of 1, 5, 9, 13, 17, and the list keeps going. Well, we have to figure out what numbers continue after 17. So it looks like these numbers go by 4s. Okay, so 13 to 17, That's 4. 9 to 13 is 4. So 17, after 17 would be 21, um, and then 25, and then 29, and so on. So 27 is not included. Okay, so this would be false because it skips over 27. And the last one says Z is not an element of the set VWXYZ. Well, this is false because Z is actually an element. It's right here. So Z is actually an element of that set. Alright, so there are 3 common ways to designate a set. We just spoke about the roster method, where you use the braces and you separate everything with a comma. We also have a descriptive method, and we have set builder notation method. So a descriptive method is where you just describe the set. So in this one, we're going to use that method to describe the set B. It contains 2, 4, 6, 8, 10, and 12. You can do it different ways. So you can say this is the set of even natural numbers that are less than 14. You can also say that it's a set of natural numbers between 1 and 15 that are divisible by 2. So there's different ways you can list this set when you're describing them. The third way you can write a set is with set builder notation, and this method uses variables. A variable is a symbol, usually a letter, that can represent different elements of a set. So set builder notation uses a variable, braces, and a vertical bar. The vertical bar is read such that. So for example, we have the set 1, 2, 3, 4, 5, 6, and this can be written in set builder notation. So this is read the set of elements x such that x is a natural number. Okay, x is a member of a natural number, and x is less than 7. Because as you can see, the numbers 1 through 6 are less than 7. We can use any letter or symbol for the variable, but it's common to use the letter x. So let's look at this example, and we're going to write this in set builder notation. So this first one says the set R contains the elements 2, 4, 6. 2, 4, 6. So you can write it as R is a set X such that if you look 2, 4, 6, these are even numbers. So I'm going to write it, let me erase that. We're going to write it as X belongs to the set of even numbers, okay, and X is less than 7. So that's one way you can write this. Okay, X is a part of the even numbers, and X is less than 7. So that would be 2, 4, 6. The next one says the set W contains the elements red, yellow, and blue. Okay, so we know X is, I'm just call it a primary color. X is such that X is the primary color. Kind of hard to list this one, but we can consider red, yellow, and blue to be a primary color. All right. So now let's look at this example, and we're going to use all 3 methods. The first one is the roster method. So we're going to designate the set S with elements 32, 33, 34, 35, and so on. Okay, so for the roster method, I'm just going to write it in. Just say it keeps going. Dot, dot, dot. And this should be a 32. I know I wrote that funny. Okay, so that would be the roster method. The descriptive method, you can say this is the set of all natural numbers greater than 31. Set of all natural numbers greater than 31. And then the set builder notation, well, we can say that X is a natural number and X is greater than 31. So I'm sorry the way I write my braces. I'm not really good at writing braces, but you understand what I'm saying. All right, so we're going to use the roster method to write the set containing 99 to 201. Well, that would be a lot of numbers to write out. So what we can do is we could just start off with 100, 102, 104. Remember, these are even numbers. We can use dot 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 to let everyone know that the list keeps going in between, and then it continues at 198 to 200. And so it'll be kind of hard to just write out 100, 102, 104, 106 all the way to 200. So if a set contains many elements, we can again use ellipses to represent the missing elements. So now we're going to talk about empty sets or null sets. A set with no elements is called an empty set or null set, and we use these symbols. You can write the braces without anything in between, or you can just write a circle with a line through it. So which of the following sets are empty? So woolly mammoths. So the set of woolly mammoth fossils in museums. So if you go to a museum, you'll likely see mammoth fossils. So this is not empty. The next one says X such that X is a living woolly mammoth. Well, woolly mammoths have been extinct for many years. So you would not find any living ones. So this would be an empty set. See, this is a little tricky because it's a set that contains an empty set. So actually, this set contains one element. So this is not empty. Okay? It's a set that contains an empty set. And then the last one, X is a natural number between 1 and 2. This will be empty. There are no natural numbers between 1 and 2. They don't exist. The cardinal number of a set is the number of elements in the set. For the set A, the symbol for cardinality is NA, N of A. That's how it's read, N of A. And it's asking you how many elements are in set A. So for example, the set R is equal to 2, 4, 6, 8, 10 has a cardinal number of 5. Because as you can see, there are 5 elements in this set. This could also be stated by saying the cardinality of set R is 5. So let's look at these problems and determine the cardinality. In this first one, set A, we have 6 elements. So the answer would be 6. This next one is X is such that X is a natural number and X is less than 16. So those would be the numbers 1 through 15. So you'll have 15 in this set. C contains one element, is 16. So this is 1. And then the empty set, there's nothing in there, so this would be 0. A set is called finite if it has no elements or has cardinality that is a natural number. A set that is not finite is called an infinite set. So for example, the set PQRS is a finite set since it has 4 members. You have P, Q, R, and S. However, the set 10, 12, 30, and it keeps going is an infinite set because it has an unlimited number of elements. The natural numbers that are multiples of 10. So that list can go on and on and on. So let's define whether or not each one of these sets is finite or infinite. We have X is a natural number and X is less than 100. Okay, so this is finite. You can count that. That's actually 99. The set R is a set of letters used to make Roman numerals. So I don't know if you know much about Roman numerals, but there are certain letters that you use to make Roman numerals. So it would be C, D, I, L, M, V, and X. So those are countable. This would be finite. The next one would be even numbers greater than or equal to 100. So you have 100, 102, 104, 106. It keeps going. This is infinite. The next one is the set M is the set of people in your immediate family. So you have certain people who are considered your immediate family, and those people you can count. So this is finite. And the last one is the set S is the set of songs that can be written. You can write many, many, many songs. Keeps going. So this is infinite. So two sets A and B are equal if they have exactly the same members or elements. Two finite sets A and B are said to be equivalent if they have the same number of elements. Okay, so the cardinality of A would have to be equal to the cardinality of B. And notice how these are written. For equivalency, it's an equal sign with a little tilde over it. So let's see whether or not each one of these pairs of sets is equal, equivalent, or neither. So the first one we have PQRS, and then we have ABCD. Well, they're not equal because they don't have the same elements, but they each have 4 elements here. So these would be equivalent. We have 8, 9, and 10, and 12, 8, and 10. So these actually contain the same elements. So these are equal, and they also contain the same number of elements. So this is both. This is equal and equivalent. The next one is 213, and then the numbers 213. Okay, so these are not equal. Even though they have the same numbers, the numbers are different. So even though they have 1, 2, and 3, you got 213 represents one number, and then 213 represents 3 different numbers. So this would be neither. Okay, this has a count of 1, this has a count of 3, and then they're not the same numbers. The next one is 1, 2, 4, 20, and then 2, 1, 20, and 11. So they don't have the same elements because this one has an 11 in here and this one has a 10. But they have the same number of elements. They both have 4 elements. So this is equivalent. And then the last one, even natural numbers less than 10, and then the set 2, 4, 6, 8. So even numbers less than 10 will actually be 2, 4, 6, and 8. So these are equal, and these are also equivalent.